basically, L'Hopital's rule in a nutshell says that if you have the limit of a function over a function, right, as that function goes to something, that is the same as the limit okay, when you get these indeterminate forms. And it's useful to use when you get things like if your original limit made it 0 over 0 or infinity over infinity, okay? You can use L'Hopital's rule, which says, hey, that's going to be the same thing as if you took the limit of the derivatives of each of those functions separately. That's great. That is the standard for L'Hopital's rule. So I want you to look at something like this. Through the magic of algebra, we can do a lot of things we've learned, right? Manipulate things into the way we want them to look. So let's suppose I gave you the limit as x approaches infinity of x squared times sine of 1 over 4x squared. Okay. Now, your rules when doing any limit is just do what first? Anytime you're asked to solve a limit, what's always the first thing you should try? Just plug it in. All right? So if I were to just plug it in, I'll do that in red. If I were to plug it in, well, if I plug in infinity to x squared, it's infinity squared, which I believe is still called infinity, correct? What do I get for the other one? Well, if you plug in infinity, first let's do the 1 over 4x squared. We've learned this. 1 over a number that increasingly gets larger, the whole fraction becomes what? So I want the sine of 1 over infinity as x approaches infinity. What's 1 over infinity? We did this a bunch of times. 0, because you're dividing 1 by a number that keeps getting bigger and bigger and bigger, so it's going to get closer and closer and closer to 0. What's sine of 0? Sine of 0. These are the things you should have memorized, like sine of 0, sine of 1, cosine 0, cosine 1. What's sine of 0? Oh. Does that... So what we have right now is a limit we can't solve. Because believe it or not, as much as you want to think that 0 times infinity is 0, it is not. No, it's not. We're not going to get into that, but it's not. There's other things you're going to find, stuff like 1 to infinity is not 1, believe it or not. All right, infinity is its own special case. So we can't just think of, oh, infinity is just any number. No. All right? So you cannot do 0 times infinity. This is what we call an indeterminate case. We cannot determine what 0 times infinity is. But as this function is written, does it follow L'Hopital's rule? Could we use L'Hopital's rule? What's the big issue with it? L'Hopital's rule says we must have what? Yeah, you need a rational. We don't have rational. We got two things multiplied together. But we do have the magic of algebra, right? On our side. So the question becomes, how can I take x? So think of x squared as my f of x function. Doesn't matter which one's what, actually, f of x or g of x. And one is my g of x function. Or it could be the other way around, okay? Please keep in mind, just because we write it as f of x over g of x does not mean the f of x has to be, it could be g of x over f of x. It doesn't matter, right? So let's take a look. How can I rewrite this limit let's see if I can get through today's short lesson with my pen, because even though I replaced the battery, it still doesn't want to work very well. How do I turn x squared times sine of 1 over 4x squared into a fraction? Number over number.
Sine of 1 over 4x squared over 1.
Multiplication of x squared is the same as division 1 over x squared. Right? And why am I picking the x squared? Because putting 1 over sine of 1 over 4x squared, can you picture that in your head, is way more complicated? I hope. So the easiest one to turn into a fraction and move to a denominator is the simplest one there, which is the x squared. So let's take it and let's rewrite it. Keep this one up here and divide it by 1 over x squared. Because it can't, again, division of 1 over x squared, you learned this one like back in 3rd grade when you start multiplying and dividing fractions. Division of 1 over x squared is exactly that, multiplication of x squared. Once we do that, think about it. If I go to solve it now, we already said when you plug infinity into sine this, you get 0, right? Now, what happens when I plug infinity into 1 over x squared? What do I get? What's 1 over infinity again? 0. All right, now I have an indeterminate form, but now I can use L'Hopital's rule because I have a function over a function. So once you get that, you can apply L'Hopital's. So sometimes when you look at a problem, you just need to work a little algebra in that problem to get it in the form to use L'Hopital's rule. That's all we did there. So let's do it. Put my LA to say I'm going to apply L'Hopital's rule here. All right, I need the derivative of sine of 1 over 4x squared. This is a chain rule problem. If you need to work it out using the chain rule, do it off to the side. It's going to be dx of sine 1 over 4x squared. However you need to get that derivative, you know how to get this derivative. It was the chain rule. We did it back. If you need to let u equal 1 over 4x squared, you can go through that whole process. So then this is just sine of u. What's the derivative of sine of u? Cosine. What's the derivative of 1 over 4x squared? We need the derivative of 1 over 4x squared. So on your paper, right now, everyone get me the derivative of 1 over 4x squared on your own. Figure out the derivative of 1 over 4x squared for me. If you need to. (1/4) x to the negative 2. That might help you. Get me the derivative of 1 over 4x squared and tell me what that derivative is. All simplified. Derivative of 1 1 over 4x squared. I rewrote it as 1/4 x to the negative 2. So what's the derivative? Tell me. Is it going to be negative 2 out front, right? Times 1/4 x to the what power? Negative 3. Right? Okay. We good with that? All right. So let's take a look. So when I take the derivative of sine x, number one, first of all, the derivative of sine is simply cosine of exactly what's there. So it's cosine of 1 over 4 x squared times 1/4, I'm going to write it this way, times negative 2 x to the negative 3. All right. I would caution against simplifying too much yet, because sometimes it's easier to cancel things if you leave them unsimplified. Now that you've done that, all I need is a derivative of 1 over x squared. Now take the derivative, because all we did here was chain rule. Derivative of sine is cosine of the exact same thing. Then I need the derivative of the internal function. The derivative of the internal function is 1/4 times negative 2x cubed. You will, especially if you practice enough, get to start using chain rule without having to write all this stuff out over here. Because you're just like, oh, I take the main derivative, then I take the derivative of the inner function. Now I need derivative of 1 over x squared. What is derivative of 1 over x squared? Yeah. Isn't it negative 2 x to the negative 3? Do you see why I didn't simplify anything? Now what? The negative 2's to the x and negative 3's get to cancel out. Boom, boom. So it equals that 1/4. When you have something like 1/4 hanging out there, you can just bring that out front. You don't need it. Plug it in. Okay, so this becomes but we said 1 over infinity is technically what? What's 1 over infinity again? Yeah, because we're working with limits, it's 0. Oh, what's cosine of 0? Answer 1/4. Done. All right. Can only apply L'Hopital's rule in this case when you have function over a function. We had function times a function. See, we had x squared times sine. Oh, well, we turned it into something where we could use L'Hopital's rule by taking our x squared and writing it underneath as 1 over x squared. Now I just get to apply L'Hopital's rule as you know it. That's it. That's all we did with that example. You do have one like that on your lab where you have two functions multiplied together instead of a quotient. You just turn it into a quotient and then you can apply L'Hopital's rule. Okay? Now there's another way we're going to manipulate to use L'Hopital's rule. Okay, this one's a little bit more complicated, but it uses some of our trig functions as well. And it's a really kind of important function to go over. This one comes when I get something like 1 to infinity, 0 to 0, or infinity to 0. Okay, all of these values. Let's go through those for a second. Okay, infinity is not a number. I know, it's more of a concept, okay? So 1 to infinity is not 1. 0 to 0, nope, not 1. I know you want to make it 1 because you're like, well, anything to 1. Nope, 0 to 0, indeterminate. Infinity to 0. Again, infinity is not a number. It's a concept. So I can't think of, oh, infinity is just any number. If I raise any number to the 0 power, I get 1. Nope, don't work that way in math. So these, again, are all indeterminate. Okay, you cannot, once you get that as an answer to a limit, you're stuck. You're not done your problem. You got to get creative then at that point. I'm going to take you through a really short, quick one first, and then we're going to do the more complicated one, and then that'll be it for these. Okay? So the first one I want to give you is this fun little thing called x to the x. Sorry. There it is. Limit as x goes to 0, I hate this thing. I think if I just go to the school and say I need a much better computer, they'll give it to me. No, it doesn't matter. They'll say, no, this one's new. We upgraded you last year. All right. So there it is. I just want the limit as x goes to 0. It's technically x0 from the right only, but don't worry about it. So that's an interesting one, because if I go ahead and plug in 0, what do I get? 0 to the 0, and I just told you that 0 to the 0 is indeterminate. So now, let's think about this. Do you remember back in pre-calc how you dealt with exponents in a much easier way? Was there a way when you had an exponent, it was like at our school was pre-calc 1 class, if you took pre-calc 1 here, if you had an equation, right, and it had exponents in it, but exponents that were variables, what did you have to do to it? Do you remember? Do you remember what you had to use? What? Say it again. Yes. Because when you have logarithms, you get to take the exponent and move it out front. Do you remember that property of logs? Do you remember this little property that said, hey, ln of 3 to the x is the same as x ln 3. That's just a basic property of logs. Exponent can be moved out front. So when we have something like that, we get to use logarithms. So the easiest way to do this, I don't particularly care for the way the book sets it up. I'm trying to set it up a little bit simpler for you. The easiest way to do this is to say, all right, I'm going to let y equal my limit. Okay. When I have something with an exponent in it, I can take the natural log of both sides. Because remember, what you do to one side of an equation is fine as long as you do the exact same thing to the other side. So we can go ahead and take the natural log of both sides. Now, the continuity of the natural log function allows us to do something that's pretty nice and pretty cool, and it basically allows us to move the limit out front and move the natural log inside. So basically the natural log of the limit is the same as the limit of the natural log. Okay? What we can do at that point is actually start to apply the property. And that becomes x ln x. All right? So I didn't really do too much. I applied two properties. One of them that it says simply the natural log of the limit is the same as the limit of the natural log. So you can switch those, which moves the natural log inside. Once I move the natural log inside, I can move that x out front. I'm only now concerned about this. I'm afraid to switch colors because my pen keeps not working when I do that, but I really want to put it in red. I want this. All right. So let's look at that. Can I evaluate that? If I plug in a 0, yeah, that's not going to work. If I plug in a 0, because I can't do L'Hopital's rule yet. Because I'm going to get 0 times infinity. That's not going to work for me, right? Because I would get 0 and then the natural log of x as x approaches 0, I believe goes down to negative infinity if you think about that graph. So I have 0 times infinity, which isn't going to work for me. But so how can I turn that into something where I can use L'Hopital's rule? Yeah, so here's the question. Which one do you want to switch? Which one do you want to leave? Because you got an x and you got an ln x. Yeah, I'd move the x. If you got like a base, I'd move that one to the bottom. So I'm going to leave ln x up top. And put that as 1 over x in the denominator. Now I have L'Hopital's rule. Now I can apply L'Hopital, because what you're going to end up with as this goes to 0, all right, technically you would end up with infinity over, oh, what's 1 divided by 0? Okay, not 0. What's 1 divided by a number that gets increasingly closer to, that gets increasingly closer to 0, right? That's what I'm going to do. I'm going to plug in 0. I can't do 1 divided by 0, but this is a limit. So what's 1 divided by a number that keeps getting smaller and smaller and smaller? Where does this whole thing go to? Infinity. Now I have an indeterminate form that I can apply L'Hopital's rule. That's what we just figured out there. That says, okay, now I can apply L'Hopital's to that. And I can say, all right, now I want the limit. When I apply L'Hopital's rule, I need to start to take the derivative of everything. What is the derivative of ln x? So that's not 1 over infinity because x is going to 0 in this problem. It's 1 over a number that keeps getting closer to 0. And as that happens, that whole fraction goes to infinity. Yeah, and it gets tricky because you're dealing with limits here, not with just plugging in numbers. Okay, what's the derivative of ln x, everybody? People are whispering it. 1 over x. Derivative of ln x is 1 over x. Okay, we've done this a lot of times. What's the derivative of 1 over x? Figure it out. Negative 1 over x squared. Because it's 1 over x, it's actually you're taking the derivative of x to the negative 1. That's where the negative comes from. And then you decrease that. So it's negative, right? X to the negative 2. It's negative 1 over x squared. Okay, so this is algebra. I need this figured out. Let's simplify that. Yeah. It becomes negative x. Work it out. That just goes down to, if you need to do 1 over x times negative x squared, you'll see that it goes down to just negative x. So what's that end up equaling? Well, if I plug in 0, I'm just going to get 0, right? And you may think you're done. I want you to look back at the beginning of your problem. Are we done? Remember, what equals 0? Natural log of y equals 0. Okay, I need to figure out what y is, not the natural log of y. This uses another property. This is a neat one. Instead of taking the natural log of both sides, what do you think? Any ideas of what we might do? You exponate, I can never say this word. Wait a minute, let me get it. Exponentiate the equation. There it is. Exponentiate means, I'm just going to take e to the ln y equals e to the 0. That's what exponentiate is. You know what's so cool about e and ln's? E to the ln of y is simply y. And what's e to the 0? That we can do, because e is a number. So, y equals 1. Y was, that's how we defined our limit, x to 0. Of x to the x. And since y equals 1, that equals 1. All that work to find out the limit is simply 1. Okay? Yes. Okay, that was the easy one. One last problem for this whole unit test. One last problem. No, my pen keeps screwing up. I don't know what I was supposed to say. Is you're just y equals 1 equals y equals z equals 1. I have no idea. All right.
Write it like that. Y equals the limit of x to the x.
I want you to realize that y was initially how we defined our original problem. So since, yeah, what are we looking for at the end of the day? The limit of x. So you, at the end, for the last thing, you have to tell me this ends up equaling 1. Yeah. We throw the y in there as a placeholder and just makes it easier to work with. All right, last problem. I'm going to go through the steps a little quicker because you've seen why we do those steps in this problem x to the x. And I'm going to go through it to figure out what the limit. And this one is going to be as x goes to infinity. The x power. First thing I want you to do is tell me what happens if you just plug in infinity to that whole problem. Tell me what you get if you were to just plug in infinity. If I just plug in infinity, what do I end up with? 1 to infinity, because 1 over infinity goes to 0. right? So I end up with 1 to infinity, and we say that is an indeterminate form. So now, I think about what I can use to solve it. The second you have an exponent, you're going to have to apply what we just did. Take natural logs, and at the end of the problem, undo taking the natural log by exponentiating the equation. That's what we're doing. So the first step is I am going to let y I forgot the limit part, sorry. I was so excited the pen was actually working. All right. There's a limit here that I can't even erase it. Come on. Come on. Hold on. Give my computer 1 second. Just give my computer a second. Don't write that because there's a limit missing. I forgot to write the word limit. And my pen that has brand new batteries in it is dying on me. Yay. Of course. Wait a minute, something happened. No. I'm sure it needs a lot of things. And it always does this to me right in the middle of a lesson. Yay. All right, so that's limit. Sorry. All right, so lny equals ln limit as x goes to infinity. All I'm going to do is switch them around. So I'm going to end the video here, and I'm going to have to attach the notes, and we're going to move to the board because this pen, and I'm going to make them order me a new pen. Look at that. Ugh.